So I will be giving a talk with the title of the Field Ready Vision, Building the Agricultural Image Repository for Sustainable Farming. Uh, this is a big project that I am a part of. I'm not the sole author of this project or the only one working on this project. This is a work done in precision sustainable agriculture, and I have been interning with the PSA for quite some time now. The problem that we are facing, and I've seen this across a couple of projects already, is that we usually don't have the quality data we need. Quality data meaning it be high resolution, if it's images, it be anointed well, maybe the names, the camera dates, anything regarding to the image. If it's a field image, then hopefully it will be having any weather effects. If it was taken on a rainy day, if it was taken on a cloudy day, any other annotation that we could have for the image is definitely helpful in training. So the main bottleneck is the data in our case. And farmers are obviously interested in knowing that what crops are growing on their fields, where the crops are growing, are there any weeds growing on the field? They want to know the moisture of their fields. Are the plants being irrigated enough, or are they being over irrigated? Are there any diseases with the plants? Do we need to add fertilizers? Do we need to change the fertilizers? What's the condition of the soil? Any uh, any like misses in the spray of the fertilizers or the spray of the pesticides, those kinds of information that the farmers are generally interested in. PSA tries to give farmers this ability to have these information at their hand and as they're needed. We do segmentation on our images for this end, and why we don't do just detection. The reason for this is that by doing the segmentation, we actually do receive more information than just detecting the plants. Detection is just having a bounding box with the four corners on the plant, and this helps in actually identifying the plant species. But by having the segmentation, we have annotation on each pixel, identifying if this specific pixel of the image is representing a specific crop or another one, or it's just a background or whatever. So it just gives us more information. And with more information, we're able to provide a more accurate end result, whatever the end goal be. So we got two types of data gathering process. The first one is the semi-field. The second one is the field. In the semi-field, the good thing about the semi-field is that it is semi-automated. So we got these big structural devices that we have designed. Actually, another team has designed. We are using them. So they go over the fields and take images like the one on the left you see here. This could be lots of pots that the plants are planted in, or it could be going over the field on a specific rails that gets images of the whole field uh, in any matter necessary. So this gives us quite a lot of images, and this spans, so each image contains multiple types of crops. It could have weeds in it. It could have different types of plants that are in the field. And it's not just a single plant that we are interested in. So while this gives us a lot of crops, it's not very specific. And the annotations that we get from these types of imaging is not related to a single crop. And it might be a bit diverse. So it's really good for development, but we can't generalize it for a single crop. And yep, so the order of the number of the images that we get are in hundreds of thousands. So it is a lot. And we use these data for pre-training mostly. On the field section, we have a couple of methods of gathering the field images. One of them is that we send an operator to the field, and the operator puts a two mats around the plant, as you can see here, along a color palette, which we use for adjusting the camera contrast and brightness mostly. After he or she puts these mats around the image, we take an image of the plant and do any type of annotation regarding the plant, so the operator can visually inspect the plant. They are relatively knowledgeable. See if there are any pesticides applied recently, see if it has any diseases, see if it is irrigated regularly, see the weather conditions that are present while taking the picture, and any such other annotation necessary. So these are very detailed, but we don't have as many images of the field section because an operator needs to go in there or a specific camera needs to be set up for that specific plant, and these are usually a lot harder to gather than just a robotic device going around the field and gathering old images. So we have like maybe tens of thousands of these images, around 10 to 20, I'd say. The usual way, the traditional way things are done in agriculture is two-way. So the first one is the manual scouting. If the farmer is interested in knowing if his crops are doing all right, he just goes to the field. He has 10 people, he sends them to the field. It's a big place, so they go on tractors, whatever. They inspect the crops, if they're doing okay, if they're not doing okay, how's everything? You need to add fertilizer. He adds the fertilizers, and so forth. As opposed to the computer vision method that we have that is being deployed most recently, is that they set up usually some kind of remote sensing. They can use some drones, they can use some cameras mounted on tractors, and then these data are gathered, further they sent to the data storage or processing units. These data are processed with the results returned, and however the application might be necessary, these are applied. So the downside to this is that it is usually a not as good quality image. There are usually a low-res images involved. They are usually power hungry, so it's not available on the edge. These data need to be gathered, processed, and the results returned for the application. And they are power hungry, so you can't just put a data center on top of a tractor and send it to the field to gather and process images, right? So these have to be processed separately. Our approach is that to be edge ready, we need relatively lightweight processing on the application level. So we use pre-trained encoders. Most of the encoders we use are trained previously, usually on ImageNet or similar large-scale dataset. So they are already familiar with the uh, image intrinsics. We don't restart our training processes. So it's not like let's gather these data and then do the training. Some kind of new data comes up. We do the training again. We get some new data. We do the training again. No, we just don't do that. We have our pipeline set up to be able to be trained on the new data incrementally, so that we don't waste energy. We don't waste processing time. And nowadays, the processing time is everything, right? Everything is modular, swappable, so one model could be doing really great on specific data conditions, specific weather conditions, specific lighting, whatever. Another model might be doing really good for our pre-training purposes or the semi-field section. So everything is really swappable so that we could change anything if necessary, and that we keep everything high resolution. So our images are around 10,000 pixels to 10,000 pixels on that magnitude. And so let's say, for instance, the residual network takes images of 256 times 256, some versions of it at least. So we don't just do a resize before we feed it to the pipeline. So what we do is that we have a tiling pipeline first, where we tile each image into a specific size, let's say 1K pixels times by K pixels. We feed these separately to the pipeline and then patch them back together to form that whole image again, if that makes sense. So the first, this is a test dataset that we first used for our training. The second one is 3, 4 times bigger than this with different parameters set. And we are going to grow this until we are confident that our latest model can do the whole size of the dataset, which is around 10 to 20K. So in this one we have 133 full-sized images. We use the tiling. We After the tiling, this 133 images turn into 3,642 train images, 455 validation, and 456 test images. The classes present are as follows. You can read them if you want. So I think there are 11 to the best of my knowledge. And the best model that we had for this one, for this run, this training sweep had 100 models. So cross a number of models, cross number of batch sizes, learning rates, different hyperparameters used. This was the best result that we had. Our unit model with an MIT B3 backbone, retrained on ImageNet weights, returned the validation DICE score of 98% and IIOU score on the validation set of 96%, which is really good. Um, so in my experience, going over the 95% is really hard. And it just shows that our annotation pipeline is really well done. This is mostly because of the high resolution tiling, so we don't lose any, especially in the segmentation. The high resolution part is really significant. We do use pre-trained encoders, the backbones are swappable, and that we prune the heavy settings early. So it's not like let's go halfway through, oh, this doesn't work, this is just there's some bottleneck or some situation comes up. No, so everything is caught early on. And we also need to use a considerable amount of augmentations. This is because the data is usually gathered in 4 to 5 states, mostly in North Carolina and Texas. So the weather conditions specifically in those 2 states are mostly sunny, which might not be the case in maybe northern states, say Massachusetts. So we do need to count for these. We add snow, rain, fog, some flares, some shadows, some blurs, any sun conditions that might be different. We change the brightness contrast, color related stuff, and also try to add a mosaic or cut mix or those kinds of stuff as well. You can see some of the images here. As you can see, at least in the bottom left one, the image is really detailed and the segmentation is done really well on the image. Uh, some of the problems that we face in these ones are related to specific crops. So some crops have like red stems, and some crops have like withered leaves or some white parts on the plant that might be due to some diseases or not, but those segmentations tend to be a bit tricky. In those cases, we first identify the plant. So let's say it's the X plant that has the red stems. Then we do the segmentation, but apply a specific post-processing to add those red parts to it as well. So our data turns out in a really good condition. And why these maps are important. So these maps are not the end goal of our research or our process. The segmentation maps are just a part of the whole process. So let's say we want to give the farmer has harvested his yield and now wants to have a cover crop or cash crop in the season that he doesn't have a yield. So we go over the field, see what his plans were, gather whatever information we needed, see what the soil's mixture is, mix it with the information from the images, and give him some options as in which cash crop he can plant now to just get the most of his field, right? Uh, if the farmer wants to spray some herbicides. he doesn't have to spray it in every plant and in high quantities. So we could have systems developed and used to have it spray only on the specific plants that have this kind of herbicides, that have that specific kind of disease. And we could also have the yield protection or the irrigation timing and those kinds of stuff as well that come as a result of our previous gathered information, which segmentation is one of. Yep. And as I said, I was not the sole author of this project. My supervisor, Matt, contributed quite a lot to this, and the other people on the project. Thank you.